Hello, this is another video to try and help you with understanding how to approach the NMR and analysis questions for A-level chemistry. This is OCR's F324 paper from January 2012. It's question 4. Starts off with some other organic chemistry and some other analysis, but the NMR is coming at us in the form of a delightful 10-mark question. Okay, very first one asks us to work out the products of this reaction we're given and to write an equation. Now, they've given you structural formulae. The very first thing I would always do is to try and draw these out. It's much easier to go wrong when you're using structural formula. If you've got it drawn out, you hopefully can start to see where the reactions are going to take place. So you're told that you're preparing an ester and it's using an alcohol, propan-2-ol in this case, and it's reacting with the acid anhydride. The most commonly mistaken or missed out part, I think, here is going to be the byproduct, which if you've got the acid anhydride, what you're going to do is you're going to break the bond here, and this section here is going to go with the proton from the alcohol, and what you are going to get is ethanoic acid as your byproduct. So that's us picking up a mark there, and now what we've got to do is bond from the oxygen of the alcohol to here. Now we've been asked to use structural formula, so I'm actually drawing this out and then I'm going to try and twist it round a little bit, and I want to try and have the hydroxyl functional group to the right hand side. So what I'm going to put is CH in brackets to have this H here in brackets, and then I can put the two CH3 groups together on the left hand side in brackets like that. So I've just rearranged it from the way it's presented, which is the OH, which is in the middle of our formula, but we want it to be on the right hand side so that we can then link it to the carbonyl to make the ester. So if I take this over here, CH3, closing my brackets there. So this has all come entirely from the molecule there. We've deprotonated it, and now we're going to bond it to the carbonyl carbon here. That will give us a CO and then CH3. So this is our ester, and this is the byproduct there, which anytime you get the anhydride, you're getting a carboxylic acid as your byproduct. Okay, on to part B. This question is all about chromatography, and it's really worth reading through all of the information. The key part here is asking how the liquid stationary phase. So normally we're used to it being a solid stationary phase, and if it is the solid, the thing that you are looking for is adsorption onto the surface, so sticking to the surface. It's not part of the question, but it's a really common thing to come up, so I just want to go over that, the D being crucial there. But for ours it's a liquid, so what we're looking for in this particular instance is the relative solubility. So you have a liquid stationary phase, you pass your mixture through it, and the liquids that have a higher solubility will take longer to pass through it, which is going to link us into part 2. Here you're given 4 compounds, an alkane, an alcohol and 2 esters, and it is an alkane stationary phase. You're going to be asked about the length of the retention times, not specifically but loosely, as to how these 4 compounds would be separated, and the key bit, how well they would be separated. So we've said it's relative solubility is the key component for separating the compounds in the mixture here. If a compound is more soluble in this stationary phase, it will spend more time stationary, so you have a higher retention time. So that's your concept for this. The more soluble the component is in the stationary phase, the more time it is stationary for. So now we're considering polarity and intermolecular forces. And the alkanes have the lowest polarity. Their intermolecular forces are induced dipole. Please don't ever write IDD in exams. Induced dipole, write the whole thing out. And the alcohols will have your induced dipole, they will have permanent dipole, and they will also have hydrogen bonds. They are the most polar, which means that here, their retention time will be the lowest, and the alkanes' retention time will be the highest. Make sure you make it clear what you're talking about there. So it's really good to separate out the alkanes and the alcohols. The alkanes would have the high retention time because they have the same polarity as the stationary phase. The alcohols would have the lowest retention time. You've got your esters here, which will have a retention time in between the two, but the crucial thing that the question is going for here, these two esters will have a similar retention time to each other, and this means that it's not very good for separating the two of them. It's not very good to work out how you could tell which ones you've got. Okay, next part of the question is the 10 marker, all about identifying a molecule here. And the GC is used together with other techniques such as mass spectrometry, NMR, to try and identify. Now the crucial part here, it is one of our esters. Always take every bit of information you can when you're trying to get the identity of your molecule. A lot of the time students here will spend so much time just trying to get the identity that they will miss marks for using all of the information given. So really show your working, illustrate to the examiner that you know exactly what every single part of the question can help you with. So, of that note, we're going to start off with the elemental analysis. You're given the percentage by mass for hydrogen, carbon and oxygen, and for each of these you divide them by the relative atomic masses. So we're going to divide the carbons 66.63 by 12, the hydrogens by 1 and the oxygen by 16. And this, I'm rounding very slightly, don't in your actual thing, I'm trying to make a shorter video for you all. You get these numbers here, and then you divide each of them by the smallest. So in this case it is 1.387. We're going to divide them all by that, and we get it to be roughly a ratio of 4 to 8 to 1. So I don't need to worry about doing anything else here. We've got 1 oxygen for every 4 carbons for every 8 hydrogens. So what this is going to give us is the empirical formula, and at this point you want to calculate what the mass of one of those units would be, and so that is what one of those would be. It would have a mass of 72. We're going to go on now and look at the mass spectrum, and the most crucial thing here is looking for the molecular ion. Now it's almost hidden there. I instantly was drawn to this peak here. Do not discount this. It's small, but it is the one of the highest mass, and that is 144. Doubt you can see that clearly off the video, but if you have the paper yourself, you will get that. So what we're going to do now is divide the molecular ion by the mass of one of the empirical formulae, just to see how many of those units fit in there. Hopefully some of you have already spotted that that is 2, so therefore the molecular formula is C8H16O2, because we're multiplying all of this by 2. So that's the marks that we're going to pick up for using the elemental analysis and the mass spec here. There is often something to be gained from the mass spec, but for this one I'm now just going to move entirely on to the NMR, and we don't need to do anything more about this one. So we are given an NMR spectrum here, And the thing that I would encourage you to do every single time when you have these proton NMR spectra is to make a table where you take the information that's presented to you in the spectrum and you use the table to make sure you don't drop any marks, and you analyse all the different parts of information that are given from each of the peaks. So listing here the peak for the ppm, you're going to, if you have it given, take the integration. So if I show you this one, I've read that to be 0.9, the integration is given as 9. This one at a ppm of 1.3, they usually have a tolerance of plus or minus 0.1. So again, if you looked at that and called it 1.2, you are going to get the mark. That one has an integration of 3. I've called this one, sorry, I should have said earlier, that was a singlet because there's the one peak. This splitting pattern is a triplet. This one, I'm calling that 2.2 ppm. The integration is given as 2, and it is again a singlet. And the last one, I'm saying, has a chemical shift of 4.2 ppm. It has an integration as given as 2. And if we look at that, that is 4 little peaks that split into, so it's called a quartet. And if I can keep with the camera, apologies there. So, there are a variety of ways to approach what you do next. I'm actually going to cover over the spectrum because I've taken everything that I need to and I've put it on here. What I want you to be doing is to be thinking of this as a puzzle where you're trying to get the total to add up to the molecular formula. So taking the information we already have, it's an ester. I'm going to also be drawing the molecule as I can down at the bottom here. We know that the ester link is this. So I'm going to actually subtract that carbon, the 2 oxygens, away from what my total has to be. And I still have to account for 7 carbons and 16 hydrogens. The oxygen is taken care of and one of the carbons is there. So we're going to use this information here. The first thing then that I'm going to be looking at is using the data sheet that you've got. Look at the chemical shifts and look and see which groups these might be. The 0.9 and the 1.3, it is RCH. So that there is always marks for just using your data sheet to work out what environment these are in. So they are really quite low ppm. These are not too de-shielded. They are the RCH environments. 2.2 and 4.2, you have environments where there is some electrons that are being removed. They've been de-shielded. Now, it's an ester. It's not got enough carbons going on here for us to have it to be an aromatic system. There's no nitrogen, so we can say with confidence that this environment here is the hydrogens that are bonded to a carbon that is itself bonded to a carbonyl. We know there has to be a carbonyl in there, so that's what these ones are. And then the 4.2, we know that there is an oxygen, there has to be something bonded to that. So we've got the hydrogen on the carbon bonded directly to the oxygen. So we're going to get some marks for spotting these. The next thing that I'm going to look at is the splitting pattern. This is the N+1 rule. N is the number of hydrogens on an adjacent carbon. So the integration tells you about how many are in the particular environment, and the splitting tells you what it is next to. I'm going to go through this just to get the information, and I'll show you how you can put these two pieces of information together. So N+1, number of hydrogens in adjacent rule, so therefore you take the number here and remove 1 from it. The singlet is 1, so there are no hydrogens on adjacent carbons there. Triplet, take 1 away from 3, there are 2 hydrogens on the adjacent carbon. Singlet is again 0, and the quartet, 4 take away 1, tells us that there are 3 hydrogens on the adjacent carbon. So, the actual environment has 9 equivalent hydrogens, and there is nothing next to them that is a hydrogen, so this is one that you have to try and learn. The way that we can get 9 equivalent hydrogens is to have a methyl group, that's CH3, and we will need to have 3 of them. 3 times 3 is 9, and these are all bonded to one carbon. So that carbon has a methyl group at the top, the bottom and the side, and then it's bonded to another carbon or an oxygen, which means it's got no hydrogens on it itself, and that's why this is the situation we've got here. At this point, what we're going to do is I'm going to spot that that's C4H9, and I'm going to take that away and know that I've got 3 more carbons and 7 more hydrogens that we have yet to figure out where they go. So there is this big group here, just if I draw it out for you just to really help you to see what we're dealing with. This is actually your dream part in an NMR question because it's accounting for a huge part of the mass and it's a really nice obvious peak. So you are hoping to see one of those, that big singlet worth 9, because it is this C with 3 CH3s on it. Okay, continuing on. The next one, it's an RCH, so you know that it's bonded to just a carbon and some hydrogens. It has an integration of 3. So this, I'm going to underline to show which one is making the peak. It's this hydrogen here, which there are 3 equivalent ones of, so it's CH3. It's a triplet, which we've already said means it's adjacent to a carbon with 2 hydrogens. So it's adjacent to that. So you see here we've got the CH3, the 3 hydrogens giving the integration of 3 being split because they're next to 2, n plus 1 makes it a triplet. Now if we see this, we then should be looking for the corresponding peak for the CH2s. There are 2 more peaks, each of them have an integration of 2, which means that they both are generated by 2 equivalent hydrogens. But these hydrogens will have some splitting. It can't be this one because there's no splitting, so it must be down here. So we have a look. Integration of 2 tells us that it's a CH2. I'm going to underline it again to show I know what's causing it. It's a quartet, which means that it's next to a carbon with 3 hydrogens. Well, that matches up. And the extra piece of information we've got, the chemical shift here, tells us that these 2 hydrogens are next to the oxygen. So we can see we've got this part of the information and then it's extended it even further along. So I could say that this is continuing there. The first peak is caused by the ones at the end and this peak is caused by the CH2 in the middle. I'm going to take away 2 carbons and 5 hydrogens now. And that means that all we haven't accounted for is CH2. Before I confirm that this matches up, the CH2CH3 is bonded directly to the oxygen. So we can put that on there. It's always worth noticing that for an ester, you can have the CH2 could have been bonded to the oxygen or it could have been bonded to the carbonyl. And you work that out by looking at the chemical shift. The chemical shift of the ones next to the oxygen directly is going to be around this region here. So that's how we know that the CH2CH3 is bonded to the oxygen rather than to the carbon. So we now know we've got this as one end of the molecule. We have this as the other end of the molecule, but we've got something in between them. So let's go through the same process. The integration is 2. So it is 2 hydrogens. The chemical shift tells us that it must be next to the carbonyl. There is a 4th bond. This has to be continuing on somewhere, but the carbon that this is bonded to cannot have any hydrogens directly bonded to it because it's a singlet. There is no hydrogens on it. So if we come down to the overall molecule, we've just noticed that the CH2 that we're missing has to be the CH2 here. Chemical shift tells us that. And it has to be bonded to a carbon with no hydrogens, which would fit with this situation here. So hopefully that makes some sense for you and you get this lovely molecule there. Thank you very much for watching.